Hi everyone, just wanted to talk with you a little bit about functions and inverse functions. So here we have a equals pi r squared. So we have area of a circle as a function of radius. And we've written it with function notation here, a equals f of r equals pi r squared. The inverse of that is found by solving for the variable r. So r is equal to the square root of a over pi, and we can write that with function notation because this is a function. F inverse of a is root a over pi. We can show that on a graph like this. Here's a equals pi r squared, but notice that this is the same as r equals root of a over pi. This one graph can show both of those functions, sort of the forward function and the inverse function. The one graph shows all of that information. So here's the graph. For example, if you wanted to know the area when the radius was 1, then you would locate 1 on the radius axis, go up to the curve, and then come across to the area axis, and that would be the value of the area when the radius is 1. If radius is 2, then you go up to the curve, you come across to the area axis, and it'll tell you the area when the radius is 2. We can do those calculations in Excel super easy. I've already got r equals 1 and 2 there. So the area is equal to pi times the radius squared. And if we bring that down, we get both values easily. To do the inverse of that, if we wanted to say we had an area of 5, and we want to get the radius that corresponds to that, we would just type equals square root of area divided by pi. And looks like about 1.26. So on the graph, we can see that if we have 5 on the area scale, we go to the graph, we pop down to the radius axis, and that's your 1.26 right there. So the one graph can be used for the area as a function of r, and also for r as the inverse function of a. Both of those relationships, they're really the same relationship, but the one graph shows all of it. When we look at the sine function, if y equals sine of x, now x is the angle, and y is the sine of the angle, which is also the y value on the unit circle. If we solve that equation for x, we would write x equals inverse sine of y. But that's not the full inverse, we know, because y equals sine x, the original relationship, is not invertible. It's not invertible because its inverse isn't actually a function. It's not invertible, we can see, because the graph of y equals sine x fails the horizontal line test. So here in red is the graph of y equals sine x. It actually continues off the screen, but that fails the horizontal line test. So that's not invertible. When we write x equals inverse sine of y, we really are only going to get a portion of the graph. And we've agreed that the portion will be from minus pi on 2 to pi on 2, or minus 90 degrees to positive 90 degrees. But notice that we haven't switched, again, we haven't flipped the graph across the diagonal line y equals x, which you used to do in MCR3U, the functions course. We could do that, but it seems to me that there's no need to do that. So we can still just use this same graph here, the blue graph showing now, to find values of inverse sine, if we want to. So here's the graph. We can use it going forward and also going in reverse mode. So if we have a value of x, or the angle, say we have an angle of 1, which would be, oh, I don't know, it's hard to find. It would be around here maybe, 1. And if you want to know the sine of that angle, you would go up to the curve, then you would go across, and you would find out the value of the sine of the angle 1. I think I've got that set up in Excel ready to go. Yeah. So here we have x is 1, and the sine of that angle is 0.8415. Okay, the graph, we wouldn't have figured that out from the graph exactly, but Excel gives us the precise value. We can do the same thing for 2. Now that's weird because 2 is actually off the blue graph. It's only on the red graph, which we can't see anymore. 2 would be somewhere, I think it's around here on the x scale. So you just have to imagine that the red graph is here, and you could figure out a y value for it. But when we want to input a y value and use the inverse function, let's actually try the same values. 0.8415, that's the value we had above. And if we want the inverse sine of that, we get almost exactly the same value. And of course there's some rounding off problems here. So what's happening visually on this graph is we're starting here at 0.84, we're coming across to the curve, and then dropping down to the x-axis to get the value of 1. It's funny, very funny, that when we try 0.9093 and we try the inverse sine of that, we get a completely different value from what we had above. I mean, we had 2 for x the first time, now we have 1.1416 this time. That's because, again, inverse sine is only a partial inverse. It's not a complete inverse of what was happening before. So what happened is we had our 2. We went up to the sine curve, which was down here, something like this, right? We came across to the y-axis. But when we feed that value back into the y-axis, let's use a highlighter this time. We feed that value back in. Now our inverse function is going to give us a value down here somewhere. So we get a different output value from this process.